Now we're going to take a look at solving similar triangle problems. First of all, similar triangles are triangles in which the corresponding sides are proportional. So for example, if we look at triangles ABC and DEF shown here at the right, we can see that side AB is twice that of DE and BC is twice that of EF. So if this was a similar triangle and we found side DF using Pythagorean's theorem, we would get the square root of 20, and therefore on triangle AC it would be twice the square root of 20 because all the sides in triangle ABC are twice that of triangle DEF. Second thing, similar triangles are enlargements or reductions of each other. So again, looking at these two triangles, to go from triangle ABC to DEF, it's half the size, so we can multiply it by a half for all the side lengths. And similarly, to go from triangle DEF to ABC, we just double all the side lengths. So one is an enlargement of the other, and one is a reduction of the other. What you also note is that the angles in similar triangles are all the same. And this is the information we're going to use to determine whether or not you have similar triangles. The next definition is a scale factor. And a scale factor is the value of the ratio of corresponding side lengths in a pair of similar figures. So we've already determined the scale factor for these two triangles. So to go from the large triangle to the small triangle, we have a scale factor of 1/2. To go from the small triangle to the large triangle, we have a scale factor of 2. So let's look at an example. Ava is standing beside a lighthouse on a sunny day as shown. She measures the length of her shadow and the length of the shadow cast by the lighthouse. If Ava is 1.6 meters tall, how tall is the lighthouse? So first of all, you have to determine if these triangles are similar. And to be similar, all their angles need to be equal. We see, or make the assumption, that the height of each, the lighthouse and Ava, is perpendicular to the ground, so that one angle is the same for both triangles. Second thing we should notice is that the angle of elevation of the sun is equal in both diagrams. So the angle of elevation is this angle right down here. The angle from the ground pointing upwards. And we're going to assume it's the same here. Assuming the sun, or assuming the measurements are determined at the same time and in the same location. So we've shown that two angles are the same, the one in green and the right triangle. Then the third one must be the same. Let's give it a symbol star. Because of the 180 rule. Think of a triangle. All the angles inside of a triangle add up to 180. So if two are already the same, the third must also be the same. So these triangles are similar. So what we want to do is figure out the height of the lighthouse using either ratios or using a scale factor. So let's start by using a scale factor. So we can see the scale factor for these two triangles. Let's say we want to go from the big to the small. The scale factor would be equal to 75.0 meters over 4.8 meters, the ratio of the shadows. So there we get a scale factor of 15.625. So the shadow of the lighthouse is 15.625 times bigger than Ava's shadow. So if we want the height of the lighthouse, so H, is going to be 15.625 times bigger than Ava. So 15.625 times 1.6. That tells us that the height of the lighthouse is 25. And in this case, 25 meters. So therefore, the height of the lighthouse is 25 meters. So that's by using our scale factor. A second way is to set up a ratio. So if we want to set up a ratio, we're going to do one triangle's side length over the other. So the way you set it up is like this. We have the height of the lighthouse versus Ava's height is equal to the length of the lighthouse's shadow over the length of Ava's shadow. So what we're doing is we're comparing the lighthouse measurements versus Ava's measurements. So what we have here are the ratio of the two heights, and here we have the ratio of the shadows. So next we need to solve this equation. So I'm just going to rewrite it down here and show my work. I need to solve for h, so I have h over 1.6 equals 75 over 4.8. To get rid of the 1.6 on the left side, I'm going to multiply both sides by 1.6. And then I can solve for h. So h is going to equal 75.0 times 1.6 over 4.8. And if you solve that, you get h is equal to 25. The same as we did using the scale factor method. All right, let's look at a second example. Use the measurements to determine the width of the river. So again, we have to look at the two triangles, and we have to determine whether or not they're similar. So there will be some angle relationships that you will need to recall from previous years, and those can be found on page 483. Looking at triangle ABC versus CDE, we should be able to show that at least two of these angles are equal. One of them is already given. We already see that this angle, angle A, is equal to angle D. However, there's also a second angle, which is easy to prove that they're the same, is this angle here and this angle here. On page 483, you would see that's called the vertically opposite angle relationship. So angles that are opposite each other, connected by two straight lines. So what we can now do is prove that these triangles are similar. So how do you prove it? So we're going to prove that triangle ABC is similar to triangle, and then we have to carefully name them. So A matches D. They're both the right angled triangle. So A and D match each other up. And then if we say B, B is this angle up here. It matches the one we don't have a label on. So that would be B and E are the same angle. And therefore, we also see that C is the same angle. So if you look at angle C here, that's both these opposite angles are the same. So triangle ABC is similar to triangle DEC. So how do you prove that? So we start off by doing this. So we say since angle A equals angle D, right? That's given in the diagram. So I'm going to put a little note there. And we see that angle BCA is also equal to angle DCE. If I want to name this angle here, that's the same as saying C here, but to give it a different notation, we start from B, we go down to C, and over to A. So that is angle BCA. Similarly, if I want to name the other C angle in the small triangle, that would go from D to C to E. So that is angle DCE. So those we know are the same because of opposite angles. So I just call it OAT, opposite angle theorem. And once we know two angles are the same, we know that angle B, the one up top here, is equal to angle E because of the 180 degree rule. Since we know two are the same, the third one must also be the same. So since that is true, then we can say that triangle ABC, and instead of saying is similar to, we can use this symbol here, which means similar, is similar to triangle DEC. And again, it's important to note that angle A matches angle D because they're both 90 degrees, so that's why I started with A. Angle B equals angle E, that's these ones here. And angle C equals angle C, that's the opposite angles given here. So now we've shown that these triangles are similar. Now we can just use scale factors or ratios to solve the problem. So we want to solve for the width of the river. That's going to be this side length here, AB. We want to find the width of this river. So what we need to do is we can use our scale factor method. So we know that this side length AC is proportional to this side length. So our scale factor, to go from the big to the small, would be 50 divided by 9. So let's start there. Our scale factor is 50 divided by 9. That's to go from the big triangle to the small. And therefore, if we want to find x, so x is going to be, well, we know that x is proportional. So here's x is proportional to the 13 side. So AB is proportional to DE. So I need to get 13, multiply it by the scale factor to get x. So I'm going to take 13 and multiply it by the scale factor of 50 over 9 equals 72.2 repeating meters. So therefore, the river is 72.2 meters wide. That's using the scale factor method. If you prefer ratios, we can set it up that way. So we have the river's width is x, and its corresponding side length is 13. So x over 13 is equal to, again, we're starting with the big triangle over the small, and then we take the 50 over the 9, the corresponding sides along the river, 50 over 9. Multiply both sides by 13, and you get 13 times 50 over 9. The same thing we got by just multiplying by the scale factor. Next example. Prove that the two triangles in this diagram are similar, then determine the values of x and y. Let's first prove that these are similar triangles. So again, looking on page 483, we have the corresponding angle theorem, or what you might have called the F pattern. We can show that this angle is the same as this angle using the F pattern. We can also show that this angle is the same as this angle using the F pattern. And if you don't see that, let's draw it here. There's my line, and there's the letter upside down, letter F. And I can do the same thing on the other side. So let's prove that they're similar. What might help with this one is if we redraw these two triangles. So let's take the first one, DCE. So there's CED. It has a side length of 6.0, 3.6, and we said that this was one of the angles here, and we said this angle here is x, or little x. And then we have this big triangle here. It is BDA. So B, D, and A. And again, this angle and this angle were the same. And its measurements, the first one actually had a side length of 6 here as well. But the bigger triangle, we take the 8 plus the 6 here. And that tells us that this is 14 centimeters in length. This is 3.6 plus y, that's taking these two, and this one down here is x. So there's a diagram of them split up. So now let's prove they're similar. So we say since we see that angle C equals angle B, and that was the corresponding angle theorem, so I just call it CAT. Angle E equals angle A, and that was also the corresponding angle theorem. And the last one, it's just a shared angle. They both share angle D. And that, you can say the 180 rule makes it the same, or you can say they both share this angle. If you look at the original diagram, they both share angle D. All right, so then we can say therefore triangle, and if we do it in order that we see it here, CED, in that order, that's the first triangle. So triangle CED is similar to triangle, and then we look at the other triangle, BAD. So triangle bad. So now that we've shown they're similar, we can use a scale factor to solve the problem. So let's start with x. So we're going to start with this. We want to figure out what x is. Well, first let's figure the scale factor. This time we're going from the small triangle here to the big triangle here. So the scale factor is going to be 14 divided by 6. So let's figure that out. So the scale factor is 14 divided by 6. So if I want to get x, remember x is being compared to this here, I need to take that 6 and multiply it by 14 divided by 6. So x equals 6.0 times 14 divided by 6, which tells us that x is 14 centimeters, which is great because notice that these two sides are the same, which means on this triangle these two sides should also be the same because they are similar triangles. So last one, a little bit more complicated, is I need to find this one here. I need to find the y value. But again, we have a scale factor. I can take this number here, multiply it by the scale factor, right? Multiply it by the 14 over 6, and it should give me this value here. Remember, it's a scale factor to go from one to the other. So I'll explain it one more time. So I want to go from here to here. These sides should be proportional. So I'm going to take this number here, 3.6, and multiply it. So multiply it by the 14 over 6, the scale factor, to get the bigger triangle. All right, so let's do that one. So we have 3.6 times 14 over 6 has to give me 3.6 plus y. So all we need to do now is solve for y. So first of all, let's multiply the left side. So this gives us 8.4 equals 3.6 plus y. And the last part is subtract 3.6 from both sides, and that equals 4.8. So we have y is equal to 4.8 centimeters. And now we're done. We have x is 14 and y is 4.8.